Good morning, everybody. I'm Sebastien LeDuc from Kalray, and in this keynote, I will talk about the usage of programmable DPUs to unlock the full potential of NVMe over Fabric and software-defined storage. So, during the last 2 decades, we have seen the data center world moving to a software-defined everything paradigm. Up to now, this has been taken care of mostly by hypervisors running on the x86. In parallel to that, a new communication protocol has been specified to fully exploit the levels of parallelism and performances of all-flash storage. So basically, the first version is NVMe, and its Fabric version, NVMe over Fabric. We believe that to fully unlock the benefits of NVMe-oF while keeping the software-defined paradigm, a new processor kind is needed, the data processing unit, or DPU. So let's start by a quick introduction of myself. So as I said, I'm Sebastien LeDuc. I'm currently Software Engineering Director at Kalray. I started my career at STMicroelectronics in 1998, and I spent almost 20 years in the semiconductor industry, working on different complex system on chips, well, mostly on software on those complex system on chips. And I joined Kalray 2.5 years ago, and I am now the Kalray Software Engineering Director. So here is the agenda of this keynote. So I will start by a quick presentation of Kalray. Then I will share some background information about NVMe and NVMe over Fabric. Then I will try to define what makes up a DPU, so what are the key characteristics of a DPU. And then I will switch to a use case section where I will present 3 different storage use cases where DPUs bring a lot of added value. And after that, we will reach the conclusion of this keynote. So let's start with a quick presentation of Kalray. So Kalray is a French public company, is backed up by industrial investors as well as by European governments. Basically, Kalray offers a new type of processor which targets the booming market of intelligent systems. This new type of processor has a many-core architecture, and it's called MPPA. And we are currently at the 3rd generation of our MPPA processor. In terms of markets, we target 2 main markets. So the first one is next generation embedded systems, and the second one is next generation data center infrastructure. So obviously in this talk, I will focus on next generation data center topic. Okay, I will now go back to some background information about NVMe and NVMe over Fabric. So if we do a bit of history, so the first NVM Express specification was released in 2011, so 10 years ago. It is a logical device interface specification that has been specified from the ground up to capitalize on the low latency and internal parallelism of solid-state storage devices. And the first specification, so NVMe, was addressing only storage devices attached via the PCIe bus. Then in 2016, we got the first NVMe over Fabrics specification released. So basically, NVMe over Fabrics extends the NVMe command set to enable using it over a network. The first specification, the first version of the specification had support for different types of fabrics, so fiber channel, Rocky, iWarp, and InfiniBand. And basically, with NVMe over Fabrics, it enables the benefits of the NVMe technology to be realized at a much larger scale than the PCIe allows. And then in 2018, the NVMe TCP specification was released. So basically, it's the version that allows to use NVMe over Fabrics over the TCP/IP network. And this is quite key as it enables to use NVMe over Fabric using existing network infrastructure. So as you can see, NVMe has been around since 2011, so for 10 years. NVMe over Fabrics has been around for 5 years. So you may wonder why now? I mean, what makes it different? Why we think it will now really start to be adopted. So first, NVMe is already being adopted. So we see a dramatic change with a huge growth in SSD adoption in the storage market. And we see that SSDs are improving at a much faster rate than CPUs in terms of performance. So this leads to inefficient processing and also to wasted storage. We can today see that the two standard ways of dealing with storage are becoming problematic. So the first one is software-defined storage based on virtualization techniques. So we see that the virtualization with the hypervisor on the x86 is now becoming a bottleneck, and it can no longer sustain the speed that NVMe over Fabric enables. And the second standard approach, basically legacy x86-based flash array solutions, we see that those solutions have a problem of price point, and we believe that there is room for disruptive solutions that will basically solve those two issues. So I have included in this slide a quote from Omdia analyst, which is planning that NVMe over Fabric will ramp up aggressively for the next couple of years. Okay, let's now try to define what makes a DPU and why it is really a different kind of processor. So what is a DPU? So in the data center, a DPU is a new class of programmable processor, which is specialized in running data center infrastructure services. Basically, it's aiming at becoming the third socket in data centers alongside the CPU and GPU. And basically, DPUs are purpose-built for accelerating software-defined data center infrastructure services. So I have named a few, given a few examples. So for software-defined networking, just as examples, I've taken virtual switching, NFV or NAT. For security, a DPU can accelerate firewall, encryption, IPsec, and of course, for software-defined storage, it can accelerate NVMe over Fabric. It can accelerate compression, deduplication, encryption, or even erasure coding or RAID, this kind of data services. So in terms of key features, so what are the key features that make a DPU? So, well, the first one is that a DPU must be fully programmable. I mean, the three planes must be programmable. So management plane, control plane, and the data plane, which of course is the most tricky one, because we are talking about high-speed interfaces and having a programmable data plane at those speeds is really a challenge. Then a DPU must have a high-performance PCIe interface because it's aiming at becoming the third socket in the server. It has to have a PCIe interface, and this PCIe interface must have SRIOV support because virtualization is ubiquitous in data centers. Of course, it has to have high-performance network interfaces with features that will allow to use and process packets coming from those high-performance network interfaces. So, for example, packet parsing, packet matching and dispatching, RDMA support, of course, some TCP offload functions like RSS, large receive offload or checksum offloads. Then the DPU must also feature some tightly coupled inline accelerators because there are key functions that are part of data center infrastructure services that need to be accelerated by dedicated accelerators in order to be able to sustain the rates, the line rates. So examples are crypto accelerators. So this is to accelerate IPsec, for example, or TLS. Other types of tightly coupled inline accelerators can be compression and erasure coding acceleration for storage. And of course, as any programmable processor, a DPU must have some security features. So just as examples, it must have a root of trust, a secure boot, possibility to upgrade its firmware securely, and a vault IP to securely store cryptographic keys. Okay, so all those features are what really make a DPU different from a normal CPU. Let's now look at the current DPU landscape. So on this slide, you can see a few companies that have DPU products today, or products that are marketed as DPUs today. So out of those, you can see three big semiconductor companies, so NVIDIA, Broadcom, and Marvell. And you can also see two smaller companies, so Fungible and Kalray, of course. So let's have a look a little bit more in details to the details of the products offered by those companies. So the first one is NVIDIA. So NVIDIA's current DPU product is NVIDIA Bluefield 2, which is formerly a Mellanox product, which got acquired by NVIDIA. So Bluefield 2 is essentially ARM octa-core CPU plus Connect X6 network interface card in the same die. So basically, they took the two and just made a single die version to get the Bluefield 2. So it features PCIe Gen 4 16-lane interface. It also has two 100 gig Ethernet interfaces. So as you can see, it seems to fit pretty well the definitions of DPUs that we gave just before. Then we have the Broadcom Stingray, which is fairly similar. Again, it's essentially ARM octa-core CPU and a Broadcom Net Extreme NIC in the same die. It is only PCIe Gen 3, and it only has one 100 gig Ethernet interface. The next one is Marvel. So Marvel has the Liquid I/O 3 DPU, which is formerly a Cavium product that was acquired. Cavium was acquired by Marvel. So the Marvel Liquid I/O has a bigger, well, it's still based on an ARM multi-core CPU. It has more core than the two previous DPUs we talked about. So it has 24 cores, which is quite big. They have a PCIe Gen 4 by 16 interface and two 100 gig Ethernet interfaces. So looking at the specification and the way they market the Liquid I/O, it seems that it's more targeted to software-defined networking than it is to software-defined storage. Okay, let's now switch to the two, let's say, challengers, so Fungible and Kalray. So Fungible has the F1 DPU. So the F1 DPU is based on a many-core architecture, so quite similar to Kalray. It has 52 Mix64 CPUs. It features 4 PCIe Gen 4 16-lane interfaces and 8 100 gig Ethernet interfaces. Okay, and now I will go a little bit more in the details of the Kalray MPPA Coolidge on the next slide. So here is a quick summary of the main features of Kalray MPPA3 Coolidge. So as I said, the Kalray MPPA3 Coolidge is a many-core architecture. So it features 80 CPU cores, which are VLIW cores. Those 80 cores are gathered into 5 clusters, and they all run at 1 gigahertz. One important point is that each cluster has some local memory, quite a big amount of local memory, which is a key feature that enables our product to be so efficient. In terms of power efficiency, it has a 20-watt typical power consumption for data center applications. In terms of high-performance interfaces, it has 2 100 gigabit Ethernet interfaces and 1 PCIe Gen 4 16-lane interface. It's fully programmable, so this is one key characteristic when the DPU is based on a many-core architecture, is that all 3 planes are fully programmable. So we have basically, in our case, the control and management planes that will run on one cluster, one of the 5 clusters. So basically, in that case, the cluster is seen as a 16-core SMP CPU running Linux, which makes it easy to port any kind of existing legacy software. And we have the data plane that will run on the 4 remaining clusters. So in that case, it makes 64 cores, and for storage applications, basically the data plane runs SPDK. So we have a software solution that is based on SPDK ported to our data plane, which makes our data plane for storage fully programmable. Okay, the next key point is tightly coupled accelerators. So in the MPPA, we have 10 crypto accelerators, as well as some erasure coding acceleration and some advanced programmable DMAs. Of course, we have all the required features for security. So be it root of trust, secure boot, or a secure vault to store cryptographic keys.